to our next tutorial on object detections. Today I'll just quickly do a brief walkthrough of some important loss functions. I believe by now you all know how important loss functions or objective function or cost function is in training models. So the loss function, it compute the error between the predicted value of your model and the actual value. That is a major piece of every model training. You have a rough idea of what the actual value is, and you need to have a way of comparing whatever your model has learned in form of a prediction, compare it with whatever is the actual value, and that's what's called the loss. And the smaller the error value, that's also loss value, error value, the better the model and the prediction. So in literature, there are a number of loss functions that are used. For example, if you are dealing with predicting numbers, which we call regression-based models, you can decide to use mean squared error, mean absolute error, Huber loss, quantile loss. But if you are dealing with classification-based models where you need to do what we call a categorical prediction, some of the loss there is you have the focal loss, you have inch loss, logistic loss. This should be familiar. It's also the sigmoid loss. There's a paper on focal loss that actually focus on that. But I feel maybe the idea it's something else. So, and you have the exponential loss. Let's see again loss function. Okay, this is a loss function for regression problem, and this defines the root mean square error, like I showed us in the previous one. And this is the prediction, this is the actual. You do a square of that and you do a square root. That is the root mean square error. Okay, so this is the formula for the root mean square error. See again. So this is the mean square error. The other one is the root mean square. This is the mean square error. It's widely used for regression and classification charts. So here, your classifier can predict continuous costs. So this is the formula for the mean square error. So this is the actual value. This is the prediction for each of the data point. When you square them, square for each data point, you sum it all through the data sample. You normalize by the number of samples. So that gives the mean square error. You also have the mean square logarithmic error. So the only difference is that you add log to each of these, and you had a 1 there. I think the 1 is to offset when your yi is it's negative also, because log of, let's say log 1 is 0. Yeah, so log 1 is 0. So I'm pretty sure you're augmenting it plus 1 to be able to maybe avoid 0 or something. Okay, let's say log of 0. Log of 0 it's uh, it's undefined. Okay, I think it's for undefined. So for instance, if your y of I is 0, they add 1 to it so that they won't be doing log of 0, which will be undefined. So you can say the same thing here. And for each data point you square, you sum up and you normalize by the number of data points. That's another one. Then we also have the L2 loss. The L2 loss function is always in use almost every time. So it's the square of the L2 norm, the difference between the actual. So the only difference between the L2 loss and the mean square error, it's just we don't normalize. You see that it's just a normalization that we take out of it, the 1 over n. That's the L2 loss. And you have the mean absolute error. Okay, in this case you discard the negative. So the actual and the predicted, if the difference gives a negative, you do an absolute modulus of that. You discard whatever negative. So that's the mean absolute error. It's more robust to outliers than MSA, and it does not make use of the square. Alright. So we talk about the L2 loss function. Now we also have the L1 loss function. The L1 loss function is the sum of the absolute errors of the difference between the actual and the target value. Let's see what makes the difference between L1 and L2. Okay, L2 is squared, but L1 is not squared. And difference between L1 and mean absolute error is the normalization. And just some subtle difference here and there. Some they put square, some they put absolute, some they normalize. And so it's the sum of the absolute errors of the difference between the actual and target value. Similar to MSI, similar to mean absolute error. Yeah. Similar to mean absolute error, except it does not have the division. So that's L1 loss. You have the cross entropy loss. We've had a tutorial on this, used for binary classification tasks. Labels are assumed to take discrete values 0 or 1. So this is your actual label. This is your prediction. This is the actual label. This is the prediction. So you put log in the prediction. So log of the predicted, log of 1 minus the predicted. You sum. This is pretty constant. Sum over all the data points. Normalize. Now here you have negative. So it measures the divergence between two probability distribution. We've done a tutorial on this. So if the cross entropy is large, this means that the difference between the two distributions is significant. And if it is small, this means that the two distributions are similar to each other. So it has faster convergence. It's more likely to reach global optimization and quadratic loss function. Then still we have the negative log likelihood loss function. So this is used in neural network of classification charts. It is used when the model output a probability for each class rather than the class level. Okay, so this is a negative log likelihood. Let's say you have like 10 different categories. You're not just going to predict 1 0 1 0 1 0 or just predict 1 at one of the class and a 0 on the other one. What you want to do is that you want to like predict a continuous number, maybe 0.32, 0.40, and everything will sum up to 1. So you already have your predictions, but you like want to scale the probability for each of the classes. So you use the negative log likelihood. This is the formula. So you have the log of the prediction with the log of the prediction. I don't know why this is the n, but the data point, and you normalize. Then you have the cosine similarity or proximity loss function. Used to compute the proximity between predictor, and this is often used in information retrieval and text mining. It also has application. Essentially, you do a dot product of your prediction and your actual, and you normalize by this square, and they have a negative. It's the same as the cosine similarity, which is a measure of similarity between two non-zero vectors. It's expressed as the cosine of the angle between them. So unit vectors are marked if they are parallel, that is if on the same straight line, or if they are orthogonal, like 90 degrees, they will be dissimilar. Then you have the hinge loss. I think that's the final loss we have here. The hinge loss is used for training classifiers. It's also known as the max margin objective. It's used for maximum margin classification. So this is the definition of the hinge loss. You multiply your actual with your prediction, and you deduct it from 1, and you also deduct it from 0. Whichever one gives you the maximum value is what you use, and you sum up over all the data points and you normalize. This is a very good piece. You often have several loss functions to train different parts. So for instance, the max out CNN is used for predicting object classes, boundaries, and uses different loss functions. You have one for regression to predict the bounding boxes, another one for the classifier. So this is very interesting and something we should have in our archive about these different loss functions and their advantages and disadvantages and their use cases. The hinge loss, the cosine proximity, negative log likelihood, Ross entropy, L1 loss, mean absolute error, L2 loss function, mean square logarithm error, mean square error, and all this. They are very important. Let's see again for the last one. So it's a loss function, it's just how the mean square error is defined in PyTorch. So you have a function called MSS, a class called MSS a loss. If you check into the PyTorch, you will see this class. And you can use the loss function. So it's a function between your inputs and your target. And you can do a backward propagation, backprop. Okay. So this is the cross entropy function in Python. If it is 1, you have negative log. If it is 0, you have this. That's the cross entropy loss function in PyTorch. Just the same thing. You just call the class. Initiate an instance of the class. Other loss function, just like we have discussed. Yeah. Thank you for listening. It's just giving us a quick walkthrough of some of the important loss functions that we would often see in paper reviews in literatures, and it's good for us to have a full grasp of what the loss function is doing and how they are implemented, what use cases are they appropriate for, and especially how they are combined in multi-task objective optimization. Thank you very much. Please do give us a thumb up and please consider subscribing for future update. Thank you and see you in the next one.